Have you ever wondered why the temperature can't drop below -273 degrees Celsius? Welcome to a journey that will take us into the realm of temperature extremes. Temperature is a fundamental concept in our daily lives. It dictates our wardrobe, our comfort, and even our survival. But how far can it go? When we talk about temperature extremes, we're not just talking about the scorching heat of a desert or the chilling cold of the Arctic. We're venturing into the domain of the ultra-hot and ultra-cold, where normal rules seem to break down. Did you know there's a limit to how cold things can get? Yes, there is a point where the temperature simply can't drop any further, and that's at -273 degrees Celsius. But why is that? So stick around as we unravel the mystery of the coldest temperature possible, the absolute zero. Scene script. Firstly, to understand why the temperature can't drop below -273 degrees Celsius, we need to grasp what temperature really is. Temperature, in the simplest of terms, is a measure of the average kinetic energy of particles in a system. Now, kinetic energy, as some of you may remember from your high school physics classes, is the energy of motion. It's the energy that an object possesses simply due to its movement. In the case of temperature, we're referring to the motion of particles within a substance. Let's imagine a cup of hot tea. The water molecules in that tea are jiggling about, moving rapidly in all directions. This movement is due to the energy they possess, their kinetic energy. The faster these particles move, the more kinetic energy they have, and consequently, the higher the temperature of the tea. Now, contrast this with a cool glass of lemonade. The water molecules in the lemonade are also moving, but at a slower pace compared to the hot tea. This slower movement translates to less kinetic energy, and hence a lower temperature. Yet temperature isn't solely about speed. It's also about how much each particle jostles its neighbors. When particles collide, they exchange energy. The more collisions, the more energy is transferred, and the higher the temperature. Consider for a moment a bustling city center during rush hour. Cars, buses, and pedestrians are all moving about, colliding and interacting with each other. This is somewhat akin to the particles in a hot substance. Conversely, imagine a quiet country road late at night. There are still cars and pedestrians, but they're fewer and farther between, much like the particles in a cooler substance. So the faster the particles move, the higher the temperature. But what happens when these particles stop moving? This question leads us to the concept of absolute zero, and that's where we're heading next. Stay tuned to find out. This brings us to the concept of absolute zero. It's a term that sounds somewhat mystical, like something out of science fiction. But in reality, it's a fundamental concept in the world of physics. Absolute zero, as the name suggests, is the absolute lowest temperature that can theoretically be achieved. It's the point at which particles of matter cease their motion entirely. Now you might wonder, how can anything stop moving completely? Well, when we talk about movement here, we're referring to the inherent vibrational energy that particles possess. Even in a block of solid ice, the particles are constantly vibrating, albeit very slowly. This vibration is a form of kinetic energy, and temperature is essentially a measure of this energy. So when particles stop moving, it means they've lost all their kinetic energy. They're at the lowest energy state possible. This state is what we call absolute zero. To put it in perspective, absolute zero is equivalent to -273.15 degrees Celsius. Or if you're more familiar with the Kelvin scale, which is commonly used in scientific studies, it's 0 Kelvin. Yes, you heard it right, 0. That's how low we're talking about. Now, it's important to note that reaching absolute zero is more of a theoretical concept. In practicality, it's impossible to completely remove all energy from a system. There will always be some residual energy, no matter how minuscule. In fact, the third law of thermodynamics states that absolute zero cannot be achieved. Absolute zero, therefore, is not just a low temperature, but a cessation of movement, a halt to energy. But why is it significant in thermodynamics? Absolute zero holds a special place in the realm of thermodynamics. It's the theoretical state at which the fundamental particles of nature have minimal vibrational motion, retaining only quantum mechanical, zero-point energy-induced particle motion. The temperature of absolute zero is precisely zero on the Kelvin scale, equivalent to minus 273.15 degrees Celsius. This concept is vital in the understanding of the laws of thermodynamics. The first law states that energy can neither be created nor destroyed, only transformed. In the context of absolute zero, it means that heat energy cannot be completely removed from a system. There will always be some residual energy, no matter how cold the temperature. The second law of thermodynamics introduces the concept of entropy, a measure of disorder or randomness in a system. As a system approaches absolute zero, its entropy tends to a minimum value. In a perfect crystal where every atom is in its proper place, the entropy would be zero. But here's the catch. This is an ideal, a theoretical limit we can approach but never truly reach. This brings us to the third law of thermodynamics, which states that it is impossible to cool a system to absolute zero in a finite number of steps. There will always be some residual heat energy, no matter how small. This is because, as we cool a system, the amount of work needed to remove an additional unit of heat increases. Eventually, it becomes infinite, making it impossible to reach absolute zero. In essence, absolute zero is a boundary, a limit that nature imposes. It's a concept that helps us understand the fundamental nature of energy and the universe. It's a reminder that no matter how we manipulate the world around us, there are laws of nature we cannot break. So reaching absolute zero is impossible. But its concept helps us understand the fundamental nature of our universe. But why exactly is absolute zero pegged at minus 273 degrees Celsius, you might be wondering? Well, let's delve into the fascinating world of temperature scales to find out. In the mid-18th century, a bloke by the name of Anders Celsius created a temperature scale which, as you might have guessed, we now call the Celsius scale. His system was pretty straightforward. He defined 0 degrees as the boiling point of water and 100 degrees as the freezing point. Yes, you heard right, it was the other way around. But later the scale was reversed to what we use today. On the other hand, the Kelvin scale, named after Lord Kelvin, was established in the 19th century. This scale starts at absolute zero, the theoretical lowest limit of temperature, and increments by the same degree intervals as the Celsius scale. But why is absolute zero at minus 273.15 degrees on the Celsius scale? Well, when Lord Kelvin proposed his scale, he decided that absolute zero, being the absolute lowest temperature possible, should be the starting point, or zero, on his scale. And since the Kelvin and Celsius scales increase at the same rate, the only difference between them is their starting point. So absolute zero on the Kelvin scale equates to minus 273.15 degrees Celsius. These scales, especially the Kelvin scale, are vitally important in scientific research and applications. They allow scientists to make precise and accurate measurements, particularly in fields like thermodynamics and quantum mechanics. And you know what's even more fascinating? Despite our best efforts, we've never actually been able to reach absolute zero. The lowest temperature ever achieved in a lab is just a smidge above it. This is due to the third law of thermodynamics, which essentially states that it's impossible to cool an object to absolute zero using any finite process. So, while we can't reach minus 273 degrees Celsius, its concept serves as a fundamental cornerstone in the world of physics. We've journeyed from understanding temperature to delving into the concept of absolute zero. We started by exploring what temperature is, the measure of the average kinetic energy of particles. We then ventured into the realm of absolute zero, a state where all motion ceases and there is no heat energy left. We also navigated through the landscape of thermodynamics and found that absolute zero is a cornerstone of this field. It's the lowest limit on the temperature scale, a point where entropy reaches its minimum value. And finally, we uncovered why this temperature limit is set at negative 273 degrees Celsius. It's the point at which the volume of an ideal gas becomes zero, according to Charles's law. And that, my friends, is why the temperature can't drop below minus 273 degrees Celsius. It's not just a number, but a fundamental limit in our universe. Until next time, keep questioning, keep exploring, and stay curious.